ideas, the fact that things has to be consistent across EM theory, and that itself leads to consistency between EM theory and special theory of relativity. So things that we have done in the first part, where we talked about conservation laws, we talked about Lagrangians and stuff, we'll see there is very beautiful inner consistencies that is there. And if you can do that, then you can basically see a lot of these things that you have done before comes out. Okay, so let me share my screen over here. Okay, so let me share my screen. Okay, so let us start by looking at these equations that we have written or derived, walked through this many, many times before. Okay, so the first one is the Lagrangian, the total Lagrangian of the particles and the EM fields. Okay, as you know this, you have now done this so many times in your homework and stuff, it should be easy for you. And the second one is basically the Hamiltonian of the particles and the fields. Okay, now if we look at this Lagrangian and the Hamiltonian, which is the total of the particles and the fields, you see there is a certain lack of unity. Okay, in a sense, when I say a certain lack of unity, in a sense, if there is an electromagnetic pulse, okay, then we have shown, or we have sort of understood that the electromagnetic pulse has a mass which is proportional to the energy of the pulse by c squared. Okay, so if we think of an EM pulse, for an EM pulse, the mass, okay, is proportional. So mass, of course, is how we define mass, and came out in a dynamical way, to its energy. Okay, so your mass was E by c squared. Okay. So that is what it is for the field part over here. So if you look at the Lagrangian Hamiltonian, that's how the mass of the fields are defined. On the other hand, if we look at the particle part, okay, charges, okay, the masses for the charges are fixed. Okay, now in contrast, the masses for the charges are fixed. Okay, and so there is no reference to the energy over here. So the way we have started, and we started with Newtonian kinematics and stuff like that, over there, the masses for the charges does not have any reference to the energy. It's fixed. So this is the mass, and then we know this is the kinetic energy, mass into half into p squared. So that's something which is sort of inconsistent in the sense that I've written L and H. Okay. Now, I think I gave you the problem where one had to calculate the momentum density, right? So there was this variation of delta T. I asked you to do a variation of delta R. That was one problem. So if you do that, so if you look at the momentum density, So let me write down momentum density. How many of you have done that, by the way? No one. Okay.
Which question, sir?
So didn't I ask you, if I remember, so I don't remember the questions to be honest. Didn't I ask you where, so this local infinitesimal conservation laws, so we worked out the energy conservation, local energy conservation by looking at the delta T as a function of R and T. But weren't a question given where you were asked to find out the conservation law when we do a delta R, a spatial change as a function of R and T? The last question, at least it is there in this, I don't know whether I gave it, did I give it in the homework? It is definitely there in the
Question 6 is there. We have to vary both delta R and delta T.
Delta T, of course, we did it in class. You have to fill up the steps, some of the steps. And delta R, we did not do at all.
Delta R is the equation of motion.
Okay, we'll see. I mean, I don't remember exactly. I mean, I remember writing it down in the notes during the class, but whether it was given, I think it was given, but I have to check. Doesn't matter. Let us not divert. Okay.
Sir, is it equals to 1 by c square a of theta?
It's okay. I mean, it's 1 by c squared. Ultimately, it will come as 1 by c squared s of that. That's what will come. We'll show that, yeah, the momentum density is 1 by c squared of energy density. That will appear, but for that one has to calculate the momentum density. I have to check the question, but to be honest, I don't remember whether ultimately I put it in. I think I had, but I don't remember. But anyway, when you write down momentum density, if you have not, if it was not there, then definitely it will be a part of your question in the next homework. If you write down the momentum density, then you'll see that over here, this is the momentum density. This G is not generator. This is momentum density. Okay. This is basically, there's a particle part. Okay. So this comes from variation, rather response to delta R as a function of R on we did delta T as a function of R and T. If you do that, then it will come, there will be a momentum density and there will be a stress dyadic that would come. Okay. Now, when we did the delta T, okay, over there, we realized, okay, remember that this is something that we have did, okay, which was derived as a variation of delta T. This came, delta T, this thing came from delta T of T and R. This is what we did in class. And this was basically, if we look at it, this was again. So we can go back, actually I can take out the notes from the previous class. I can bring it out and you can show. This was This is what it is. But this EI was basically half MI BI squared. So when you compare these two relations, again, when you compare these two equations, you see if you compare this, comparing you see that your G total is total by C squared. Okay. And so this thing itself, this kind of relation is also valid only for the field part. So this is for the field. But this is not for the particle, the way we have done till now in Newtonian mechanics. So in Newtonian mechanics, we'll not get the momentum by looking at the energy and divided by C squared. Okay. So this is not there. Okay. So there is in this particle part of the total Lagrangian and the field part of total Lagrangian, there is a bit of, let's say lack of uniformity. So one solution is that the Newtonian mechanics is of course responsible for this. Okay. So this is only for field, not for the particle part. And one way of thinking is that the Newtonian mechanics is responsible. Okay. And maybe the correct relation between mass and energy, maybe the correct relation between mass and energy is basically M is C squared. So of course we don't know this yet, at least for the particle part. So the idea is, what if we believe that this is the correct relation and make it, as universally valid? So let us try to use, let's try to make this relation universally valid. Okay. And let's see how things change if we sort of impose this criteria that no, this must be the correct relation, so that both the particle part and the field part behave in the same way. So what we propose. So this is what I would propose, that let's say we take a single particle, and for a single particle, in the absence of electromagnetic fields, so single particle, absence of EM field, okay. Our proposal is that the momentum, okay, this momentum is mass times velocity, right? mv. Right? So our proposal is P is equal to E by C squared. This is a proposal. So mass is not a constant. So we propose that mass has to be an energy dependent thing. Okay. And let us see what's the consequence of having this. Now, once we have this, we are going to go back and rework some of these things by looking at equations of motion. Okay. Now remember in Hamiltonian mechanics, so in Hamiltonian mechanics, we have V as del H, del P. Okay. So this is del E, del P then. Okay. So this, if I use this Hamiltonian mechanics, then this will lead to, so if I use this and the previous equations, then what we get is we'll have a C squared P dot okay. So we can integrate this. Right? Just from this ansatz, we get this, use Hamiltonian mechanics, we integrate this, and what we are left basically after integration is that C squared P squared plus a constant. Now this constant is 0 for the electromagnetic pulse. So this constant, is 0 for the impulse. Okay. For the particle, the constant has to be some energy when the momentum is 0. For the particle, when P is equal to 0, the constant has to be some energy, because left-hand side is energy, so constant has to be some energy. Okay. And this, because energy is related to the mass, it has to be related to mass. So you will have some, when P is 0, this E is minimum. So you'll have some E which minimum. Okay. That will be something, some mass times C squared. Because this was the proposal that we started with, right? It has to be from here. This is what you wanted. So rest is very simple. Therefore, we have E squared is C squared P squared plus E squared minimum. Okay. And you do the things. This is basically C squared P squared plus M prime squared C4. Okay. So now, of course, since this is related to the mass, we could denote it by some mass of the object. Okay, we can denote this thing, we can denote it by the familiar M0, which is the rest mass. Because that's what P is 0, it is at rest, the rest mass. I hope we can, I'm writing very badly, I hope you can sort of understand. So your E squared gives you P squared C squared plus M0 squared C4, okay? Or you can just get rid of this and then basically say this is your energy. Okay. So remember, we got this energy again very simply by dictating that just like the electromagnetic pulse, for consistency in the Lagrangian, the particle part should also have a mass which is energy dependent and defined in the same way of E by c squared. And that immediately, using the fact that Hamiltonian dynamics is applicable to the particle part, gives you this relation of energy, the momentum, and the response of the particle. Now, we had momentum as E by c squared v, right? This we had. So therefore, I can write it down like this. So therefore, P squared c squared is equal to E squared by c squared v squared. Okay. So now if I look at this equation, so this equation and this equation, okay? If you look at these two equations, we see that what we should have is by E from these two equations, we see that my energy is m0. So if I just combine these two equations, we'll see that energy is m0 c squared plus 1 minus v squared by c squared. Okay. It's something that is familiar, how the energy of a particle increases, okay, when your velocity changes. Similarly, the momentum is again the 1 minus v squared by c squared. Okay, so this is what it is. So one thing you obviously see that over here in the second case, when your v is less than c, your momentum, of course, is your Newtonian momentum. Okay. And from consistency, it turns out that if we have a consistent relation between particles and fields, then the momentum cannot be a Newtonian momentum. The momentum over here should be the one where you have a velocity dependence. Similarly, for the energy, when V is less than C, okay, then your energy basically gives you your m0 c squared plus half m0 v squared. So you have the rest mass energy, which always has to be there because the mass is there, and then the classical kinetic energy of the particle. Similarly, for P, when the momentum is much less than m0 c squared, okay, then energy can again be written as m0 c squared plus p squared by 4c. These two are equivalent. So this is at the low velocity term. What happens when you go to the high velocity case? Okay. So this is what happens. You have, this is the general relation, and this is the low velocity case. What happens if you go to the high velocity? Now we know that however the velocity increases, velocity cannot become larger than the speed of light. That's one of the postulates. Okay. So for V approaching C, okay, velocity cannot be greater than C. So in this case, what happens is that we enter a new domain. Okay. in a new domain. So previous domain was the velocity was much, much less than c. Now over here, we are going to a domain where the v is approaching c. In this case, what we have is basically c, let's c over v squared plus m0 squared c squared. This is again from your energy and momentum and mass relation that we've written at the first step. So as you can see, this is actually an inequality. In general, over here, there is this is equal, is actually a less than equal to 3. So velocity is always less than equal to this case. So when your rest mass is 0, then the equality happens. So then your velocity is equal to c. And when the rest mass is not 0, the velocity is always less than c. So things that we did before in a different way, the dynamics, these masses, the energy and the momentums were changing. That now comes over here from a very different consideration, that the field and the particles must behave in the same way. So by imposing that the particles should also have an energy dependent mass just like the fields have, we end up with this dynamical view of the, so modifications of the Newtonian mechanics, Newtonian dynamics. But we should not stop over here. We can move a little more further. Okay. So given this, so over here, let me write, equality is only for m0 equal to 0. So now let's change color. So let us work out the Lagrange Hamiltonian dynamics. Okay, the Lagrangian Hamiltonian dynamics. What happens if we already sort of keep on moving in this way? So remember, the Lagrangian in that mixed form, there's 3 forms, right? Was P dot dr dt minus d, okay, plus half np squared plus dr. Let us omit the potential part. So we're only talking about free particle, no potential over there. So let us omit this part. Okay. Now, this basically means we have this, okay. But over here, what we have is half mv squared. So this is the Newtonian thing. And we have seen that this doesn't make sense now because we have actually modified ourselves and gone beyond the Newtonian by, again, as I said, by demanding that the particle part of the Lagrangian and the field part, they behave the same way in terms of mass. Okay. So we cannot just have half mv squared. Okay. So it has to be replaced by some function of velocity. Okay. So replace it. So it has to be some function of velocity. That's what it has to. So we have to modify it. So we don't know what this function is. Of course, we have to find out. So my Lagrangian then over here becomes P dot dr dt minus V plus some function, plus some function of velocity. Now, recall that this also implies that my Hamiltonian, okay, and in Hamiltonian also you're going to get rid of the potential part. The equivalent Hamiltonian would be basically P dot V, okay, minus half mv squared. So over here it will be P dot V minus some function of velocity. Okay. So now what we're going to do, we are going to put in the form of the P and the E. Okay, Hamiltonian is of course E. Remember, this is E. So you already know what is my E and P. We're going to put it over there. Okay. We're going to put it in this Lagrangian of E and P. So when you do that, so put your E. So your E also depends on your velocity. Your P also depends on your velocity. So now, okay, substitute E and P from above. Above means from here. From these equations. Okay. So if I do that over here, so my E, I substitute E, I substitute V, then we'll see that my f of V, okay, this is equal to m0V over 1 minus V squared by C squared half dot V minus m0 C squared over 1 minus and so this is nothing but minus m0 C squared 1 minus squared by C squared. So that is your f of V. So instead of a half mv squared, you have a new form that is consistent with this approach that we are taking. So if you go to the Newtonian limit, where V is much less than C, you will see this will be a half mv squared plus m0 C squared. Okay. So this f of V for V less than C will be basically f of V will become minus m0 C squared plus.
So minus.
Yes, Nikhil?
Minus half mv squared.
Minus half mv squared, yes. Yes.
Also, sorry, it will be plus both.
It is plus, exactly. Plus, because there is a minus inside.
Yeah.
Yeah, it is plus. Okay. Now, if I want to check consistency, that this form that I have written for f of V, what you have got, whether actually it is consistent in the Hamiltonian dynamics that we had, right? So for consistency, what we must check, just like over here, remember, where did you write down the, where did you write down the del E, del P? system, yeah, over here. Just like we had in the Hamiltonian that your V has to be del H del P, remember? Okay, so we must try to find a similar consistency over here. Okay, so for consistency, we can calculate del FV del V. Okay, this should be obviously be equal to P, right? So if you do del V of this equation of minus m0 c squared this to the power half, do that, you will see that this is basically, so your Hamiltonian equations are also consistent. Now, what we can do is that we can, when we did this Lagrangian in actions, remember, we had these three forms where we can write it in the Lagrangian form, we can write this action with the Hamiltonian form and the mixed form. If I want to go into the Hamiltonian form, we have to eliminate the V. So if I want to go into the Hamiltonian form of the action, okay, so someone who has not followed these classes will suddenly hear this kind of things and what is saying Hamiltonian form of the action. But you know, we have looked at the three forms. So we can eliminate my V, we can eliminate V to get the Hamiltonian form. Okay. So over there, my L is basically P dot dr dt minus H with H being c squared p squared plus m0 squared c4. So what we have done is something which is very interesting, right? I mean, by demanding that the particle part of this electromagnetic action behaves the same way as the field part, from this consistency argument, we have actually got new particle dynamics, right? So we have got particle dynamics that we get for Einstein's relativity. So we have moved away from the the dynamics of Newtonian dynamics into Einsteinian dynamics by just demanding that in the Lagrangian that we wrote, or the Hamiltonian that we wrote, the two parts must look at the masses in the same way. The masses that we have for the field, which depends on the energy, should be same, or the masses for the particle should behave in the same way. Okay. So we got this new dynamics, this modified dynamics, just from demanding consistency. Okay. Now, what we want to do further is, now we should push this further and show that if we have this modified dynamics, then it also means something of how your time and space coordinates change. So basically, we want to look at Lorentz transformations. So what we'll see that this modified dynamics and some more consistency relations will actually force us towards the Lorentz transformations that we had. So we are doing it in the back way, in a sense. Things that we have done previously is not like this. We are talking about internal consistencies over here. So now let us look at what happens if I have this dynamical form and apply this to systems viewed from two different frames. Okay. So now let's go to some Lorentz transformations. Okay. So change of color again. Okay. So let's towards Lorentz transform.
But sir,
Yes.
we assume that the energy and the momentum should have some specific form for this, right?
Energy and the momentum. We
Have
just
some. We assumed that, right?
yeah. So we demanded, right? So because for the electromagnetic wave, the energy and momentum had this mass was energy by c squared. We demanded the same thing over here. We didn't do anything else, right? Look at over
Yeah,
here.
we assumed that thing, right? And after assuming that, we will get the Lorentz transformation from
Yeah. No, the only thing we assumed was this thing. This m is e by c squared. That was the thing that we assumed.
Yes, sir. That's what I'm saying.
Yeah. And that assumption came, or rather, we wouldn't say assumption. Let's say imposition is a better word. We impose this. We basically said that, look, here is a Lagrangian of the total system, which is divided into two parts. In one part, when we are talking about fields and we have calculated everything, we see that this thing holds, that mass is energy dependent. But in the other part, the way we have started from Newtonian mechanics, the mass is not energy dependent. So let us impose that the mass is also energy dependent over there. And let us find out what happens. So we imposed, we didn't assume, okay? It's even stronger than that. We imposed it. And once we impose it, that the two parts behave in the same way with respect to the mass, then it turns out, consistency tells you that your energy and masses has to be related in this way. This equation follows from there. Only then it goes back to your low energy regime of Newtonian mechanics and any energy regime of your Einstein mechanics. That's the whole thing. So now let us try to move forward and try to do Lorentz transformation. Okay. So again, two coordinates. Okay. Let one coordinate have a small velocity with respect to the other. Okay. So there's a delta v velocity with respect to the other. Okay. So if I took any point, then the r of that point in these two coordinates that changes with time, because one coordinate has a small velocity delta v, right? And it grows linearly with time, because the delta v times t. That's how this small r is changing. The difference of, take any point over here, okay? The r from here and the r from here, look at the delta r is changing linearly with time. So let the movement have a delta v, let the coordinates move, one of the coordinate system move with a small velocity delta v, okay? Then what is happening is that the coordinate translation, okay, goes linear with time. Okay. So two frames move with respect to each other with some constant velocity. So two frames move with respect to each other. Some constant velocity. And just take a single particle. You can do it for multiple particles later. Just take a single particle. So what we'll have is my delta R thing. This is delta V. So the delta R, the change of the coordinate, this translation is a linear with time, and it's multiplicative with this delta V. But remember, we have, because we will be doing dynamics at the end of it, we also have to see how momentum changes in these cases. Okay. So not only the coordinate is changing, momentum is also changing. So there is also a momentum change. And this momentum change, if I look at it again, this is just what we have imposed before times delta v, because there is a change in the velocity. So when I have so over here, the momentum and the coordinate change is due to change in the coordinates, okay? But whatever be the change, it basically means if I change my R and P, I'm changing my action. So the coordinate change is giving me a change in R, is giving me a change in the momentum. It also means it introduces a change in the action. Okay. So these two, so there is a change in the action, some change in the action. So what I want to do now is to see what is the change in the action due to this coordinate change. So let us calculate delta S, okay? This delta S is due to a change in the coordinate and the momentum, okay? And this is LDT. So what is the change in LDT due to the small change in R and P? And this, so I'm going to get rid of this R and P now. Remember LDT, you could write down in the previous thing, I have written it down over here. L is P dr dt minus H. So just put that L over there. Excuse me. This is equal to delta of P dot dr minus H dt. Calculate this. So just work it out. This is P, okay? So dr and dt you basically put in. So this is P dot C squared delta P dot dr minus this, and this cancels. The delta S is basically H by C squared delta V dot dr. And what I can do is I can take it, do it like this. I can write down my delta S as H, and then a differential of 1 by C squared. So to do this, what I used was I used the relation between C. So I have used to do all this thing. What I've done is that I have used this relation of C squared P TP is equal to ED. And also I've used del H del P is equal to PC squared. So the main thing is I get this relation. Okay. So get this relation where my change in the action due to the two changes in R and P due to the change in the coordinate gives you this. Now, I'm going to do one more imposition, just like I imposed before. Suppose, other than this delta R change,
Sir,
yes,
what is dV here?
sorry, say it again.
What is dV?
I still can't get you. Nikhil.
dV. What is dV? So write delta V dot dV, right?
No, not V, R.
Oh, sir. Oh, sorry.
Sorry, this is R. This is all by quick handwriting, horrible. This is R. Okay. See, this is R, delta V dot dr. Okay, this is not V.
Sir, fine. Fine.
Okay. So now we do one more imposition. So we impose one more thing. Okay. Like change in like delta R, we vary time. Okay. So that is, we have a delta T. But let us say that I impose again that my time variation, delta T variation, is 1 by c squared delta V dot R. Okay. So this is an imposition. Remember, I impose this. I'm saying that let my time variation delta T be 1 by c squared delta V dot R. So this is almost by definition. This is I'm imposing. Okay. Then this time variation, then this time variation will also change, give you a delta S. Okay. And the delta S contribution that comes from this time variation. So delta S, let's see, let me say T over here because of this time variation. And this is basically minus H D of delta T. So now look over here. Because of this imposition, remember this is imposed by hand. Because of this imposition, the change in the action due to the time variation is this. And the change in the action due to my coordinate transformation, which gives you a delta R, which basically gives you a delta P, that was this. Okay. So the net variation of delta S, when there is a variation of R due to moving of the coordinate system, if I impose a time variation like this, okay, then the net variation net variation, which is delta S, let's say total, which is basically delta S RP plus delta S time, this is equal to 0. And so something very interesting has happened over here. I've imposed this, that let my time variation be this. Given this imposition of time variation, my total change in the action is 0. It basically means the action is invariant. So this means the action is invariant under a combined space and time variation. What combines space and time variation? The space variation should be delta R is delta V times T, and my time variation delta T is 1 by C squared delta V dot R. So if I have a combined space and time variation like this, the action is invariant, which basically means the dynamics is invariant in a coordinate transformation if the time also varies in a certain way. So the coordinate transformation gave you a space variation, but by imposing the time varies in a certain way, I have the action invariant. So in this both these coordinates, your dynamics is the same. So what you have got over here, and you should realize this immediately, that this is nothing but Lorentz transformation. So these are infinitesimal Lorentz transformation. Okay. So whatever Lorentz transformation did before, this is exactly the same. The finite Lorentz transformation that you saw, that you're familiar with, this comes from this infinitesimal Lorentz transformation if you can continuously add this infinitesimal Lorentz transformations. Okay. So if you have multiple small infinitesimal Lorentz transformations, you will get a finite Lorentz transformation. So by this imposition, remember all these things came up because we had m by c squared as mass. We had dynamics, use those dynamics. We found out that this dynamics and the fact that action remains unchanged, which basically means in coordinate transformations, there's two coordinates, you have the same kind of dynamics. That comes only when space and time, they are combined and they vary in a particular form. Okay. So let me give you a homework over here. Okay. So let me give you a homework. So, okay, first of all, let's say, these add up to the familiar finite transformation. So your homework is exactly that. Homework is exactly that. So let me write down what the homework is. Okay. So your homework basically is prove the above statement. Okay. So what you do is you take your delta V, okay, along x-axis. Okay. So that basically means it's only moving on the x-axis, so there is no change in delta x or delta y. So delta x is basically 0 is equal to delta y. Okay, and your sorry, what did I say? I should not say x-axis, I should say z-axis. And your delta z is equal to delta v by c times t. Here delta ct is equal to delta v by c times z. think I'm doing it right. Others I will check. Now you basically say that these changes are due to some continuous, there's a parameter, you continuously change the parameters and you get this kind of changes. So consider it's basically something like this. So consider the infinitesimal transform as a result of changing a parameter. Let's say call it theta. So basically you say that your delta theta is your delta p by c. So you keep on changing your delta theta, you get a change in your delta v. Okay. So using this, you write down differential equations for, so you write down differential equations, okay, for all these coordinates. So basically you have your write down dx theta, d theta, you have, you know, dy theta, d theta, then you have dz theta, d theta, then you have dct theta, d theta. You'll have differential equations. Then you solve these differential equations with proper boundary conditions that you have to impose. I'm not going to say what the boundary conditions are. And when you solve these differential equations, you will find that you will go to a second order differential equation. So this is the integral. You will find that what we'll find ultimately is that when you solve, then show that you get x prime is equal to x, y prime is equal to y, and your z prime will be your familiar z plus vt divided by 1 plus v squared by c squared to the power half. Okay. And your t prime is equal to t plus vz by c squared. And then again divided by 1 plus v squared by c squared to the power half. So these are the Lorentz transformation. So you can actually start from this infinitesimal Lorentz transformation, solve the differential equations, and you'll show that you'll get these finite Lorentz transformations that you have been familiar with. And finally, okay, for these finite transformations, you also show that r squared minus ct squared is equal to invariant. This is an easy thing, of course, trivial. Okay, that's one homework. Now, for this infinitesimal transformation that I have shown over here it is quite easy to show that this r squared minus ct squared is invariant. Okay, this is quite easy to show. So if I start from over here, okay, I can basically just take, so if I want to show that r squared minus ct squared is equal to invariant for infinitesimal. This is very easy. You just put in put in the equations for this delta v and delta r from before. So what you have is you want to take this r squared minus ct squared, okay, or ct squared minus r squared, doesn't matter. This will be, you'll see that this will be 2, so this will be minus 2 t delta v dot r minus r dot delta v. This is automatically. So for this infinitesimal transformations, the fact that this d tau, which is r squared minus c squared, this tau squared that we have introduced before, that is invariant, that immediately follows. Okay. There's one more thing that you could do is go back over here. Because your total action is 0, which means due to this Lorentz transformation, there is a conserved quantity, right? There is a conserved quantity due to this coordinate movement. Because remember, the action is 0, and that will give you some conservation law. Okay, the invariance of the action means some conservation law. Okay. So this is another homework. It's 2 homework from today. Okay. It's not difficult homework, it's easy homework. Okay. So show that the invariance of the action due to delta R and delta T, okay, implies a conservation law. Okay, so remember, if you go back, you have to go back quite a few classes, and remember when we had this kind of Lagrangians, there were these things which we call generating functions, which was related to conservation laws, this G, okay? So your G was basically P dot delta R minus H dt. Okay. You take this generating function and you show that the result conservation law is the very famous try it. It's not difficult. Okay. So what we did today, I'm not going to move with the third one because we don't have much time over here. We'll start with the next one. What we did today was that we tried to basically write down Lagrangians, total Lagrangian, total action in a way where the field and the particle, they behave on the same footing. And once we do that, we found out that we automatically get the Einstein modification, the special zero derivation of the Newtonians, high velocity modification of the Newtonian terms. And then we realize that if we have this small change in coordinates, and over there again, we use the same dynamical principle that your P is basically has a mass dependence. So your masses comes as E by C squared, not a constant mass. Then we can have the action due to delta R and the change in action due to delta T in such a way that the action remains invariant if you impose a certain change in the delta T. And which basically shows you, if you basically change the space part, space change, and the time change due to a coordinate transformation, in a certain way, your action becomes invariant. And so you come up with some transformations where your equations of motions are the same in both the coordinates. And that turns out to be a Lorentz transformation. And as a homework, I also show you that this kind of transformation basically also leads to this very famous conservation law, which is this mass energy conservation law. Okay. Because we started from over here, right? It goes back to over there. So this is what we're going to stop today. I don't want to start something new after this. Next day, what we're going to do would also be very, very interesting. So we are going to, so till now we have used Lorentz transformation, fine. I mean, we have showed dynamics, masses, and then we have showed that Lorentz transformation. Next day, we're going to show that your EM Lagrangian, that is invariant under Lorentz transformation. Now, again, remember what you have done before is that trivially you have basically written down Maxwell's equation and you have then used Lorentz transformation, the finite form Lorentz transformation, to show that, oh, the Maxwell equation is the same. Okay. That is something that I've done before. We are going to do it in a slightly more technical form because now you're used to this jargon and these ideas. So we showed in previous things how we have local conservation laws, how locally if we have this delta R or delta T, small change locally, how your Lagrangian changes, okay, and what comes to it. Over here, we are going to use the same formalism to small local Lorentz transformation, small local change in coordinates, and show that the entire Lagrangian, not only the field Lagrangian, but the total Lagrangian will be unaffected. And of course, I'm not going to, it has a lot of steps. I'm not going to work out through all the steps. If you have done the delta R by yourself and filled in the form for the delta T that I did before, you should be able to do this exactly the same way, same kind of steps. Okay, but just for this kind of changes where your delta R has a specific form of delta V times T and delta T has a specific form. But you will show that this does not change your total action. So that we'll do next day, and then hopefully we'll have time. That will not take the full class. So then maybe we'll do a couple of problems, and then we can continue with that. Okay. Now, you guys, whoever have not yet submitted your assignments, please submit. So it's showing 16 people have submitted in Moodle. So there are still a few more people who should be submitting. Okay. So please submit, because remember, all of you have been given enough time to complete it, and your deadlines are over, and I'm continuously, the next assignments will come very soon, next week. So please submit it. Okay. So that's it. I'm not going to do anything right now anymore, and we'll stop here.